Think about the old saying, garbage in, garbage out. For decades, this principle has been the golden rule of data science. It tells us that if your input data is flawed, your output results will inevitably be flawed. We have built entire careers on this foundation. We spend hours scrubbing datasets, removing outliers, and normalizing values. We treat every corrupted record as a threat to the integrity of the model. But what if I told you that in the modern age of artificial intelligence, this rule is actually broken? We are entering an era where messy data can produce gold. This is not magic, it is mathematics. Specifically, it is the theory of benign overfitting applied to high-dimensional spaces. For a long time, the logic behind garbage in, garbage out made perfect sense in low-dimensional settings. Imagine you are trying to predict the price of a house. You have a few variables like square footage, number of bedrooms, and location. If you feed the model a square footage number that is wildly incorrect, the prediction will be wrong. The signal is fragile. In this environment, data cleaning is essential. The noise drowns out the truth because there is not enough room for the model to distinguish between the signal and the error. Every variable carries a heavy weight. If one fails, the whole structure wobbles. This is why we have always been taught to treat data hygiene as the primary driver of success. But the landscape of data has changed fundamentally. We no longer deal with a few variables. We deal with thousands, sometimes millions of features. This is what we call high-dimensional data. In this new reality, the geometry of the problem shifts in ways our intuition cannot easily grasp. A recent theoretical framework from 2026 argues that garbage in, garbage out fails for high-dimensional tabular data possessing latent structure. This is a profound claim. It suggests that predictive robustness arises from the data architecture rather than item-level cleanliness. It posits that diverse, error-prone variables can asymptotically overcome noise through a mechanism called informative collinearity. To understand this, imagine a library where every book is written in a different language. Most of the text is gibberish. If you read one word, it means nothing. But if you look at the entire collection, you might find a pattern, a hidden structure connecting the words. In high-dimensional data, we often have this. We call it latent structure. It means the noise is not random chaos. It is correlated in a way that preserves the signal. The errors are not independent. They talk to each other. They cancel each other out in the aggregate. This allows the model to find the stable signal buried within the chaos. The architecture of the data itself provides the robustness that traditional cleaning methods try to manufacture. This phenomenon is mathematically linked to benign overfitting. In the past, we believed overfitting was always bad. If a model memorized the training data, it would fail on new data. We thought fitting noise was synonymous with failure. But in high dimensions, things change. We see a phenomenon called double descent. As you increase the complexity of the model, error goes down, then up, and then down again. In the final phase, the model fits the noise perfectly, yet still predicts accurately. It seems paradoxical. How can memorizing noise help you generalize? The answer lies in the geometry of the data. The model uses the extra dimensions to push the decision boundary away from the critical points. It finds a stable path through the noise. This is why the principle of garbage in, garbage out fails. The model is not fooled by the noise because the noise has a structure that the model can exploit. Consider the implications of this for how we build systems. If we assume garbage in, garbage out holds true, we waste immense resources cleaning data that is actually useful. We spend millions on data pipelines to scrub every single digit. The new theory suggests that data cleaning is not the primary driver of success. Instead, identifying and exploiting latent data structures is the prerequisite for robustness. We need to stop treating every noisy variable as a liability and start treating it as a potential asset. The capacity to generalize from noisy inputs becomes more important than the purity of the inputs themselves. This is a fundamental shift from data hygiene to data architecture. There is a consensus gap in the scientific community regarding this specific reversal of the garbage in, garbage out principle. While the core theoretical argument is detailed in the primary research and associated repositories, broader validation remains ongoing. A separate study on time series linear models confirms that benign overfitting applies to dependent data under specific covariance conditions. This supports the broader theory, even if it does not address the specific GIGO reversal thesis directly. The absence of independent replication in all cited literature highlights a knowledge gap. We have a strong theoretical case, but the broader community is still verifying the extent of this paradigm shift. This means that while we can turn garbage into gold, we must be careful to ensure the latent structure is actually present. It is not a license to be sloppy, but it is a license to be bolder. The future of artificial intelligence depends on our ability to find signal in the noise. We must prioritize identifying and exploiting latent data structures over strict data cleaning. As models become more over-parameterized, the ability to leverage high-dimensional latent spaces becomes the new competitive advantage. We are moving away from a world where we demand perfect data. We are moving toward a world where we demand perfect understanding of the data's geometry. This allows us to build systems that are resilient to the messiness of the real world. The traditional necessity for exhaustive data cleaning is being challenged by the reality that diverse, error-prone variables can overcome noise through high-dimensional inference. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.